So I will be using this book, Understanding Machine Learning, as a first step. So it has quite some theory. And the framework is statistical learning framework. Okay. So a little bit of statistics will be needed, but then I will explain things as we go along. Okay. So when we think about learning, so I will go with very basic stuff, okay, because I don't assume anything about machine learning from you. So I will go with very basic stuff, like what exactly learning is, okay. When a learner tries to learn something, then what are the inputs that the learner needs, right? And obviously, what will be the output? In this case, it will be prediction, okay. So it could be prediction of classes, it could be, we will see, like there are wide-ranging applications of machine learning, but we will formulate these things first in with a set of notations and things like that. Okay, so what we will study is something called statistical learning framework. Statistical learning I will use chalkboard only. So let us look into what does learner needs, right? Okay, so learner's input. So learner needs some domain set, okay? So basically some data, okay, based on which a learner will learn something, right? So learner's input would be, let's say, a domain set. And what are the typical notations of a domain set? If we use it, let's say, X, okay? And these are the set of objects we wish to label, okay? So we wish to label, okay? So as an example, it could be a set of images, and then we would like to say whether that image has a cat or not, okay? So example, given an image, label it as cat or no cat. Okay, basically identify whether the image had a cat or not. So this is what we call label, okay? So given a sample, we will say, okay, label it. So okay, whether it's cat or not, okay? So domain set will be set of objects. In this example, set of objects will be set of images, okay? But then we can think of this as many other examples also, okay? This could be paragraph of a some textbook and something, and then we may want to label it as, okay, that paragraph is about some topic, okay? So let's say something from maths, like that paragraph is about compactness of a set, okay? So given a text, right? Given a text, label it in terms of topic, right? So let's say as let's say it's a compact set definition, something like that, okay? Since we are mostly from maths, we will see a lot of examples from there. Okay, so so learner needs a domain set, essentially set of objects that it wants to learn, okay, or label, okay. Okay, so sometimes in machine learning, the domain set may have different names also, okay. So for instance, it may also be referred as also referred as instance set, okay. So the objects in this domain set, okay, can be called samples, can be called instances, okay. So objects in X. Okay, so let's say this is our domain set notation. X are called let us say instances. Okay. Sometimes we will also call it features and so on. Okay, so sometimes we will also call it features, feature vector, because everything at the end of the day will be made into vector. Image, it's a pixel. If it's a gray scale image, then it's a 2x2 matrix. So basically, image can be referred as like this set of pixels, and this pixel value tells you the intensity. Okay, in black color. Okay, so we can say it's a 0.5, okay, 1 or something like that. Okay, depending on how we have these pixel values, right? So grayscale image can be seen as a 2x2 matrix, but then I can make it into a one long vector, and then I can have color images, but then color images I need RGB values. So red, green, blue combined can give you in certain intensity. Okay, combined can give you a color. Okay, so the color images are like tensors. Okay, color images, and grayscale images are 2x2 matrix. Of course, I can always make them in a vector. I go row by row, let's say, and here also I can make them into a long vector. Okay. So an image can be seen as a grayscale image can be seen as a vector. If it's color, then it also can be seen as a vector. So this one vector will be there like this. Okay, so the whole image data will be a vector of pixel values, and then here you will say what it is. Okay, so whether it's a cat or not. Okay, so everything will be encoded like that. So if it's a text also will be encoded as a vector. Okay, so for a text, okay, so if I write some text, okay, so let us say I am learning machine learning. Okay, I'm learning machine learning. Okay, so this is some text. Then one can say, okay, this is the text. Then how can I make this as a vector? Well, you can do some encoding. You can do word encoding. So in your dictionary of all the words, you can give some number to each of the words, right? So here I can give some number to this word, some number to this word, and so on. So this is like word encoding, word by word encoding. I can also do character-wise encoding. So this character will have some number representation, and then this will have some representation, this has some representation, space will also have some representation. So again, I can make this into one big vector like this, and then I will say, okay, what this text is about. Okay, so the learner's data could be set of images, could be set of text. Okay, it could be anything arbitrary, right? I want to predict the housing prices. So houses come with, sometimes they come with gardens, sometimes they have 2 floors, sometimes they are 3 floors. Okay, size of the houses. So all this can be put as a feature, right? So so let us say how many bedrooms are there, right? So one data. Okay, what is the size of the bedroom? What is how many balconies are there, and so on. Okay, so I encode this as some form of data, and then here it could be the price of the house. Okay, so here again it will be a prediction problem, but here it may be a little bit different than these. So here we were saying something in terms of discrete, whether something is cat or not, whether the text belongs to some topic or not. Here the price can take continuous values. Okay, so this becomes like a logistic regression, and this becomes like linear regression problem. Okay, we will come to that in detail, But in the context of this, a domain set for a learner, it could be set of images, it could be set of videos, it could be audio, anything. Okay, they will be represented as some vector, and then these are the labels. Okay, so we understand now what is domain set. Domain set is essentially any set of things that I want to learn, okay, encoded as vector. Okay, okay. So now let us look into the labels. Okay, so and the notation for labels. Okay, so label set. So initially, what we can do, we can simplify our life and say that labels are, let's say, binary. So it's cat or not. Okay, so if it's cat, I encode it as 1. If it's not a cat, then I encode it as 0. So it's a binary class problem. But as I said, if I am taking images of multiple images of let's say animals, okay, then it could be cat, it could be dog, it could be some bird. Okay, so there can be many classes, right? So then 0 and 1 won't be enough, right? But let us say we consider only 2 class problem, then label set we can encode this as 0 or 1. Okay, so restrict to 0 1 set for the moment. Okay, or this 0 1 if you like. I mean, this is just a number. Okay, so it's not necessary that it should be 0 or 1. It could be like -1 +1. Okay, and so on. Okay, so if we introduce an example of a papaya, then in this context, okay, so go to some island and there is a lot of papayas there, and then your goal is to identify a papaya is ripe or not. Okay, I mean, it's a tasty or not, right? So then papayas will have certain features, right? So again, when you do machine learning, it's always have this kind of 2 types of tables. Here you goes the feature, okay, and here goes the labels, right? So then when you are learning whether the papayas are tasty or not, you will look into certain features of papaya, right? So it could be softness, okay, color, okay, there could be many more things, right? So then you will go around the island and you will look into various papayas and you will measure their softness. You have some measure of softness, you will encode this as a number and you will put them, and then in your data, some of these papayas you will maybe test them also. Okay, so for certain softness and color, and then you say that it's ripe or not, okay, or it's like tasty or not. Then you take another papaya, check the softness and color in some form. Okay, let's say you have a way to measure all these things, and then in some cases it may be not tasty. Okay, so you will have a data like that, and then you will build a predictor function, okay, for a new papaya. Okay, this is where you knew about these, right? Okay, so this is a label data. For softness, color is there, I know what it is. Another set of softness, color, I know what it is. And the machine learning problem will be, now I will give you a new papaya, and then based on softness and color, you have to predict whether it's tasty or not. Okay, so in the case of papaya, again it's a 2 class problem, okay, tasty or not. So we can stick to this binary class problem. It's a 0 1 problem. Okay, so initially we will stick to papaya as an example. Okay, so as I already told you that we build some kind of training data. Okay, so what we have seen is that we have a domain set, the set of objects that we want to learn, that's X. Okay, and then corresponding labels for that. Okay, so in this case, this is our X and this is our labels. Okay, so together combined, it will be called training data. Okay, okay, so let us define training data. Okay, so now we combine this. Okay, so training data will be the pairs x. Obviously x is like more, x is just not a number, x is a vector, and in this case y is one number, but even y could be multiple. That will be multi-level problem. Okay, so a given text can be okay, so there is something, let's say Twitter. Okay, so someone writes something on Twitter and you can say, you can do the sentiment analysis of the Twitter. Okay, so you can say, okay, with this Twitter text which is encoded as this set of features, and then you will say, okay, this Twitter person looks maybe surprised, unhappy. Okay, so then the levels will be surprised, unhappy, and so on. So that's called multi-level problem. Okay, and then we have a multi-class problem where it could be cat, dog, and so on. Okay, what we are doing right now, it's binary. Okay, something is there or not there. Papaya is tasty or not tasty. Okay, image has cat or not cat. It could be dog or something. We don't care about that, but whether it's cat or not, we are just worried about that. Okay, so now we will write down what is training data. Okay, so training data, as I said, is a pair x, y. Okay, so training data, we denote this as S, which is x1, y1, x2, y2, dot dot dot, xm, let's say ym. Okay, so here m means how many samples I had, how many instances I had. Instances, features, samples. Okay, so in machine learning people use these terms. Okay, so sometimes someone will tell you how many instances you had in your data. The same question they will ask, how many features you have in your data, how many samples you have in your data. Okay, so here you will say m. Okay, so each x1, y1 is one row in your data. Okay, y is your level. Okay, so these are our y, y1, y2. For x1 sample, I have y1 level. For x2 sample, I have y2 level, and so on. Okay, so here I have m labeled samples, or so in our training data, the number of samples is m, and there is a concept of how big is your x. Okay, I mean x itself is a vector, right? So x itself is a vector. Now in this case, x has two components. Okay, and so this we call it as a feature dimension. Okay, so the feature dimension of x is 2. Okay, so feature dimension of x is 2, but if it's an image, right, image classification problem, then the feature dimension will be the number of pixels I have, right? So let's say it's 512, let's say it's 16 by 16 image. Okay, 16 by 16 pixel image. Then since you are making them as a vector, it will be 16 times 16. Okay, that will go here, right, in the case of an image. So your feature dimension will be 16 times 16. Okay, yeah, initial one will be basic, but very quickly it will go into maths. Okay, so okay, so this is our training data, and m represents the number of samples in our data. Then what is the length of x? In this case it's 2, that we call it a feature dimension. Okay, so it depends on the problem. Okay, for images feature dimension could be bigger, for text it could be even bigger, and so on. Okay. Okay, so this is the notation for us. Usually features are denoted by x, labels are denoted by y. So these are pairs in the Cartesian product x, y. Okay, so if we use curly y as set of labels, in this case it's we stick to binary, then it's 0, 1, and x are the samples. Okay, so they come from a Cartesian product. So we have defined training data essentially. Okay, what are we trying to learn? What are the notations we use? Domain set, okay, and then the label set, and combine they give me the training data on which I want to implement some learning algorithm. Then the next thing is learner's output. So essentially, yeah, I mean, in this case, learner will try to learn something. Okay, in this case, it's papaya is tasty or not, or so on. Okay, so learner's output. Okay, so learner, what does learner learns? Learner learns this prediction rule. Given this, how is going to predict this? Okay, everything about machine learning. I mean, unless you go to the generative modeling that we will do tomorrow, generative modeling is more about imagining, okay, creating something new. That's another class of problem. But here, it's a pure prediction problem. Okay, so majority of the machine learning problems are like that. Given a data, can you learn a prediction rule to predict something? Okay, so that's what learner is going to do. Okay, the learner output will be some to learn some prediction rule. So learner learns prediction rule. Okay, and in this case, again, our goal is to introduce the notation, right? So let us say that prediction rule is some function x that takes samples and it produces labels. Okay, so here h is called the prediction predictor. Okay, so here h is called predictor. Okay, so it's important to like get used to these names. Okay, it's called hypothesis. In fact, we will use hypothesis a lot more, okay? And or classifier, okay? If it's a classification problem, then obviously it will be called classifier. So obviously the goal of the predictor is to predict about a given data, okay? So predictor predicts the labels of new data, of new domain point, okay, or so domain point or sample or instance. Okay, so we have to get used to this these similar words, same words basically. Okay. So for papaya example, learner learns to predict, right, whether the papaya is tasty or not. So that's the rule a learner has to learn. And we can use a notation AS as is the hypothesis that algo A returns on data S. So we have used a notation AS. It's like we apply our some algorithm on our sample or the training data, okay, label data, which we have defined there S. So some algorithm that gives me the hypothesis, okay, meaning H, okay, for a given. Obviously, for a different training data, your hypothesis function will be different, obviously. So if I'm taking a cat image data, then the predictor function that I will learn will be different. If I'm taking a papaya being tasty or not problem, then there the predictor function that I will learn will be different. So H does depend on S, okay, which is the training data. Okay. Okay, so we are getting used to the notations here. And in general, these instances, okay, or the training data that we get, we believe that it comes from some probability distribution. Okay, just like any data, there is some underlying distribution. So cat images coming from some distributions. Okay, papayas are coming from some distributions, and so on. Okay, so so we will put a remark on that. Yeah, maybe use this again. And then once we define this, we will get to a little bit of a learning theory. Which are the things learnable, okay, when it's learnable, when it's not learnable, and things like that. So we can define a probability distribution, okay. So denote probability distribution over X sometimes I may not use like curly kind of X, but it's the same, okay, X that I need, right? Okay. So what we know, so we are going into like even more formal things, that any training data that we believe that it comes from some distribution. Okay, let us say that's the distribution of the data. Okay, and obviously we don't know as such. Okay, initially we don't know. Okay, okay, when we train it, we will kind of predict which distribution it might be coming from. Okay, not explicitly that I will tell you, okay, this is distribution, but implicitly, let's say. Okay, so during prediction, obviously, like my prediction function has to kind of somehow implicitly know, okay, or learn this. Okay, okay, so learner in general doesn't know about the distribution, okay, or that's obvious. So learner does not know about D. I mean the learner is exactly trying to find, at least implicitly trying to determine that, right? Okay. So for labels, we assume if I am giving a label, then the problem could be in the labeling itself. So when I created the data, right? So maybe some weird guy went into the island, and for him or her the concept of tasty maybe is very different. Okay, so the labeling itself may go wrong. So it depends on which training data, how the training data was created. Okay, so but if we keep that aside, we can say, okay, let us assume that the labeling that happened was like correct. Okay, so we assume a correct labeling, okay, function. Okay, so labeling itself can be seen as a function. So given an X, we get Y. Okay, this is when you create the data. Okay, so someone went to the island and started taking samples, softness, color data, and then labeling them. Okay, that's when you're creating the data. Prediction is when see a new papaya, okay, then you predict. Okay, so based on this data you have learned the H, okay, prediction function, and then based on the new data you will predict. Okay, so the first step itself is labeling, and let us assume that labeling is correct, and that we denote it as F. H is the something that we learn to predict. F is something that we use to label the data. Okay, so yi is fxi for all I. So we have given the labels for each sample or instance. We have given the corresponding label y. This assumption itself can be relaxed a little bit, and that might show in the bound as well. Okay, so the fact that we have a correct labeling may be relaxed, but it may have an impact on the learning theory outcomes. But for the moment, we can write this as a remark. So this assumption can be relaxed. Can be relaxed. We will see how. Okay. For the moment, let us assume our data is pure. So obviously, learning function is unknown to the learner. I mean, this is what the learner is trying to find anyway, right? Learner is not aware of the learning function. Okay. I mean, the problem is that this data can be the field data, right? You physically went there in the island, you plucked these papayas one by one, you find them tasty or not. That was a prediction, that rule inherent in your tongue maybe, right? Your tongue identifies perhaps something as tasty or not. That was your labeling, right? But what we want is the machine to kind of predict based on the features, just by kind of like looking or maybe even touching a little bit, because softness you need to touch a little bit, and color maybe. So okay, so what we say is that f is the correct labeling function, which could have come via some hands-on data collection techniques. Okay, but machine has to kind of figure out this H prediction rule. Okay, so yeah, I mean, if your H becomes F, then yeah, I mean, you are perfect, right? Unless the F itself was not perfect. Okay, okay, so okay, so now so until now we can summarize what we have. Okay, so in summary, each point in the training data is generated by sampling xi according to d. Remember, d was the distribution, right? And labeling it by f. Labeling it by f, where f was our labeling function, right? Okay, so we have this setup, right? We have domain set. Okay, domain sets are denoted by x, and we call them instances, samples. Okay, and then for each of these instances we have the labels, okay, which we denote it by y. If it's a binary class problem, then we have 0, 1, plus minus 1. Okay, whatever you feel like, 1, 2, 100, 2000, doesn't matter. Okay, there should be some label, okay, that distinguishes 0 and 1. And we combine domain set and the label to get a training data S. Labels, giving labels during collecting the training data is called labeling, and for the moment we assume that is denoted by F, and it's a correct labeling procedure. There itself it might go wrong. The underlying distribution of our data is denoted by D. Obviously, D will change depending on which data you are working with. Okay, so these are this is the setup we have now. We'll like kind of prepare to go into theory. So the question is, given a correct labeling function, if I am going to build a prediction rule which is H, okay, that I wrote before, how much error I am going to make? Okay, so what is the measure of success? Okay, so we need some measure to check whether our learning process is correct, okay, or correct up to some error, okay. So then we need to define something called measure of success. So let me define it here only. So this is basic machine learning setup. These things everyone should know, but we will gradually move into more interesting, deeper ideas later on. So let us first discuss what is measure of success. So let us define something called error of a classifier. Error of, okay, this is how we are going to measure the success. So this is the probability that classifier does not predict the correct level on a random data generated by distribution D. So that's how we define error of a classifier. Okay, so error of a classifier is the probability that the classifier that we learn, okay, does not predict the correct level. Okay, so what is the probability that I'm not going to predict the correct level? I will measure that. Okay, okay. So maybe it's with 0.2 probability, let's say. So in other words, I take 10 samples, okay, new samples, okay, or let us say 3 samples also, okay. Out of these 3, it predicted here correctly, and here it was wrong, here it was wrong. Okay, it can happen. Then in this case, I will say it's like 1/3 probability. Okay, it's predicting correctly, and in other 2, yeah, 2/3, it's not predicting correctly. Okay, so this is how we are going to measure the success. Okay, again, you can ask after learning the predictor, how do you know to check whether it predicted correctly or not, because you don't know about these anyway, right? So usually what we do is that we have a training data, we train only on some part of the training data, we leave the other one to check for the correctness. Okay, so we call it test train split. Okay, so let me write this. So x1 itself is a vector, remember, okay, and then we have y1, and then we have x2, y2, and so on. And let us say we do it up to xk and yk, and xk plus 1, yk plus 1, and xm, ym. We keep this as a test data. Although we already know the levels for this, we keep it out from the training data. We train our model to predict some hypothesis H. This hypothesis, the prediction rule, okay, we will get into specific examples how these prediction rules are constructed. For the moment, it's abstract thing. So let us say we find some H from this trained data. Now we will use this on this and see whether it predicts this correctly or not. From there, I can kind of say, okay, the error of my classifiers out of, let's say, m minus k data, in how many of them it predicted correctly, that will give me the error of a classifier. Okay, so number of corrected divided by the total number of the test data will give me the probability of success. Okay, or if you want to do the error, then how many cases it failed divided by the total number of test data, it will give me the probability that it did not predict on those. Okay, so you can do it both ways. So this is how we can measure. Okay, so usually in machine learning, this is what we do. Any training data, we will split into test and train. We build our model, and then we check our model on the test data. Okay, and if you are doing bad on test data, you will go back and you will improve your hypothesis class. Okay, usually these are parameterized models. So what does learning theory tell you is that there is no generic H. Okay, there is no generic H. You have to go with some inductive bias. Okay, and by that what I mean is that you have to pick a template. You have to pick a template. There is no universal function that will give you a rule to predict to predict in all the cases. Okay, so we will come to that in a more rigorous way, but you will be achieving some template. Okay, there cannot be a generic template. Okay, the generic template doesn't work. I will give you a very specific example where generic template won't work. But so you will come with something called inductive bias. Inductive bias means that although I will have a template, but this template will be specific with some modifiable parameter, and I will tune that parameter based on the data, okay, and then I will see whether it does prediction correctly or not. Obviously it may go wrong, but if it goes wrong, then I will go back and see, okay, the template that I used may need to be changed, okay, a little bit, or maybe completely. It depends. So these inductive bias that we set in our hypothesis comes from some experience also and practice also, but there is no generic. I mean, we can prove that also, okay, that you cannot have a generic predictor function at all, okay. We can prove that. So you will always come with this inductive thing, bias. Inductive bias here means choosing a template, okay. That template will have parameter that I can tune to get a correct predictor function, and then from there I will predict. Okay, so what I'm trying to say is that it is possible that we will make error, and that error might be coming from the prediction function that we have used as a template. So that template itself may be not correct. The whole idea behind machine learning success is that the templates that they have got right now, which are so-called neural networks, are so powerful that it works, okay? Because in general you will say, okay, I mean, you are talking about template, but this is like, I can have polynomials, I can have some combinations of arbitrary regression, I have like kernels. So there are so many functions that can act as a predictor, right? The success of recent machine learning, starting from around like 2000 onwards, it's mostly because of neural networks, because neural networks are a very powerful template, okay? It's so powerful that it's like everywhere, even like playing chess, okay? So you play chess, even they will use machine learning, because out of these so many possibilities that you have, it can kind of predict a correct move for you, and it beats the best players in chess, okay? And there are like other probabilistic ideas also, like Monte Carlo research and so on. But in most of the problems, machine learning, the power is coming from neural network. These are the very powerful hypothesis class, okay? Otherwise these problems were not very new anyway, okay? So understanding neural networks, even doing optimization method, which learning a predictor function is an optimization method. We will see this tomorrow, okay? So hence we need a separate course in itself just to learn how optimization method can be used, okay, to learn this H, okay? So since, as I said, these are parameterized networks, there will be parameter theta here in the model, and optimization will be over some loss levels and minimize over this theta, okay? It's a very high level thing I'm telling you. If it doesn't make sense, it's okay. We will see this after this semester, or you will be expert in many things. So for the moment, let us say that, okay, we are supposed to build a prediction function. This prediction function itself can be used, but there is kind of a generic framework like neural network. Still there are like specifications there, okay? So if I'm working with images, so let us say I'm using neural network. If I'm going with images, then people have figured out, okay, maybe you go with CNN kind of thing, okay? If you are working with text data, okay, so let us say machine translation, okay? So English to French, Hindi to English, okay? So these you will use maybe RNN or even recent ones now, LSTM, transformers, okay? So yeah, I mean, even the generative models are, the neural networks are also kind of like so if I want to do generative modeling, which is another course, it's like as if you will get a complete picture of everything, it seems, by the end of this semester. Generative model is a whole course we will study. Okay, so we will go to diffusion model and so on. Okay, so it's the whole course in itself. Okay, RL is something in this lecture series we will touch at some point. And then training of these is optimization method. Okay, as I said, that's another course in itself. So what I'm trying to say, coming back to this, is we are interested in learning a prediction rule. And recently, I mean, neural networks were proposed long time ago, but they became popular because of the computing resources that came, like GPU and so on. So it's easier to train these networks. Okay, so with the advent of neural networks, I have a kind of a generic framework. I won't say very generic, because again, if I'm going into some specific applications, then there are some variations, but they are all, you see, they are all neural networks. Okay. So that's why things became very, very interesting now. Okay. So yes, so when we are learning this, we will make errors. Okay, for sure, because there will be image that you have seen in the training data, but there may be a new image of a cat which looks similar to a dog or something, right? Then maybe you will make error there. Okay, so it also depends on the training data. Okay, how much information was there in the training data, so that it learns very well. Okay, okay. So we have defined measure of success, and so let us now define few notations here. So we can define something called domain set or domain subset actually. Okay, so domain set we have already defined. Let us say domain subset is A, which is a subset of X. Okay, and it follows the probability distribution D. Okay, and we have also defined so let us say define a number. Let us say assign a number dA. Okay, so define a number dA which determines how likely it is to observe a point X in A. So we have these notations that we will need in the proofs. Observe a point X in A. So this is the notation we have, that so dA means how likely. So here again it will be some kind of a probability measure. So how likely it is to observe a point X in A, where X is something in X. Okay. Okay. Okay, so here we can refer to A as event, can refer to A as event as follows. So define pi from X to 0, 1, then A will be set of all X in X such that pi X is 1. Okay, so and the dA can be written as, so these are some notations right now. dA can be written as probability X d pi X. Okay, we define a probability measure pi from X to 0, 1 and we define A to be set of all x for which pi x is 1. Okay, so then it becomes some set A. Okay, and then dA we can write this as, again this is another notation here. So probability of pi x. Okay. So now with this notation we can define something called error of the prediction rule. Error of prediction rule. So we can define L df as our error, and this is defined as p x sampled from D, and wherever hx is not equal to fx. So that's okay. We are defining an error is probability whenever the prediction rule that we learned h is not equal to the labeling function f. Okay, so that exactly is the error, right? Our prediction rule is not matching the correct label. Okay, so we define the loss function like that. Okay, L D F H. So in text this means probability of randomly choosing an example x for which, I mean it's the same thing but just kind of writing this in words. Okay. So here df subscript, this one df which is the subscript, it denotes it means that the error is measured with respect to distribution D and the labeling function f. Okay, so means error is measured in distribution D with label function f. Okay, so we are getting used to notation. I mean there's nothing, no big deal here, but just like these notations like D, F, all this makes sense. Even at some point we will get rid of the D because D we don't know. Okay, so we have to go with the sample distributions. Okay, the realist what we have in hand, what we collected, right? So that will be called empirical loss. This is like a true loss. Okay, but for true loss you need to know the D, but you don't know. So you will always work with only empirical loss. True loss is not possible. Okay, so we have defined this loss. Now yeah, we will define few things like generalization error, empirical risk. Okay, so when you read paper they will always keep saying empirical risk and so on. So here L df h is, there are few terms. Okay, so this is called generalization error. Generalization error, or it's called risk. So in this case it's just called risk, but when we will calculate loss on like the samples, okay, then it will be called empirical risk, because there is some other term which we will define that will be called empirical. This is just risk. Okay, and sometimes called true error. As I said, true error is usually not possible, okay, because you don't know the underlying distribution anyway, right? So okay, but this is what you want to achieve in practice. You want your generalization error to be as less as possible. The term generalization here refers to the fact that I have worked with some data and I have kind of learned some prediction rule, So this outputs some prediction rule H, and by generalization we mean whether H is able to now predict correctly on the new data. Okay, and that's what generalization means. So can it generalize? Okay, so that's what machine learning community will say. Oh, you've built a prediction function. Can your prediction rule generalize? Meaning, on a new data, does it make less and less error? Then we say the generalization error is very less. We say risk is less, true error is less, things like that. Okay, but as I keep saying, true error you may not know, because however many cat samples you take, that is still finite. The true distribution may be infinite. Infinitely many samples may be there. Okay, so we will be working mostly with empirical one. Okay, but it's good to know. Okay, that these are the. So what are the information available to the learner? So information available to learner. Well, information available to the learner is not really D, because that's the true distribution. Okay, learner also doesn't know F, because learner just got the label data, but the learner doesn't know how to label, obviously, because if he knows how to label, that will be exactly the same H he is looking for. So, so the information available to the learner is certainly not D and F. Okay, so learner is blind. Okay, is blind, or is like unaware to D and F. Learner knows only about the training data. Okay, xi, yi. So learner only knows about training. Learner only knows about training data. Okay, so that's pretty clear. So what learner can do is not this. Learner don't have hand on D and F. So learner has to specify some other loss based on the data. So that will be empirical loss and so on. Okay. So let us define now the empirical loss. Empirical usually means experimental. Okay, the word empirical means experimental. Okay, so empirical risk. Minimization. So since D and F are not known to the learner, an error can be calculated only from the training data. Okay, so since D, F are not known to learner, an error can be calculated. An error that can be calculated is only the training error. Calculated is only the training error, because essentially those are the data that he has access to anyway, right? So remember, we use the notation S for the training data, right? So S was this pair x1 y1 ... xm ym, right? So essentially we have to build a loss based on this training data. So there will be S coming in place of D now. Okay, so we can define LS of H. H is the prediction rule that learner learns. So this is the learner knows about that. Obviously H was built based on S. Okay, so this we can define this as says so this will mean the cardinality. So I in M, so this M is the index set. So this M here means set 1 to M. Okay, so this is a set index set notation. So this means 1 to m index. So I is one of these, okay, 1 to m. And obviously we know, right? So the training error will be h of xi was not equal to yi. Okay? So for which of these I, h of xi is not equal to yi. So that's how, and how many of those? So this is the cardinality notation, right? For how many of those? So that's what we are going to do. So h of xi is not equal to yi. Okay, so the count these, okay? That's what it means. So this is something learner can has access to, okay? The learner knows this, okay? Because build the h, xi's are already there with him, or he can just check whether they are not matching and take the count of that and divide by m, the total sample. That's how you get the probability, right? So number of samples where it didn't predict out of total number of samples m. Okay. So we saw generalization error, risk, true error, and for this loss we will have some specific terms. So this is called training error, or empirical error, or loss, or empirical risk. All are same terms. Okay, all are same things. So this is what you will use in practice to check check whether H, the prediction rule that you learn, is correct or not. So empirical risk minimization is a problem of discovering H for which LSH is minimal. Okay, so that's called empirical risk minimization. So here I can define that. So empirical risk minimization. So this is called ERM. Okay, when you read machine learning papers, books, there you will see this all the time. Okay, so empirical risk minimization. This means coming up with H. Okay, the prediction rule H that minimizes LSH. LSH, the empirical risk. Okay, training error, empirical error. Okay, these are same terms. So the whole point of machine learning is to do empirical risk minimization, ERM. You are given a set of samples. Okay, you will come up with an H such that the loss on the training data is minimal. Now, coming up with this loss, the H will encode some function here. It will be some parameterized function, a complicated one, as I said, neural networks. And you will build a loss. So in this case, I built a loss in terms of kind of like, yeah, probability and so on. But later, I will build a loss specifically where I will take a difference or something like that. Okay, I said, okay, I not equal, but maybe like how close I am. And there will be a parameter theta here, let's say. So this difference, this I will measure a parameter theta here. I will minimize the loss over theta. Theta is the handle I have to tune my hypothesis. Okay, and that's called machine learning training. And as I said, this will be an optimization problem. Okay, minimize over theta. Now, depending on whatever H we take, the optimization algorithm may change. Okay, if you go to generative model, it becomes min max. Okay, so all these things we will see in detail later. But this is the formalism of machine learning models. Okay, so there could be a few issues. Okay, obviously while training. Okay, so there is something called overfitting. Okay, so let us see some examples of that. I will give you a very abstract example in the beginning, and later I will give you more kind of intuitive example on that. Okay, so let us see the problem of overfitting. Okay, so ERM can fail miserably. Okay, that's what the book says. Okay, so let us first put this in a bullet. ERM may fail miserably. Okay, and we demonstrate a failure case. Okay, so we demonstrate. Okay, let us see this, and I have one more, and I have like some sample points which are represented as dots, and this outer one we call it area 1, area 2 actually, and inner one is area 1. Okay, so I am demonstrating a case where things may fail. Okay, let us see how. Okay, so we have these two boxes, concentric, one is inside, one is outside, and we have these dots which are our instances or the samples. Okay, so it could be anything, like it's a toy example. So let us see. These samples are like, if you want to really give numbers, then let's say it's x-axis, y-axis. So these are some coordinate pairs. Okay, so they become your feature. Okay, so these are some coordinate points and spread out uniformly. Okay, so instances are distributed uniformly, let us say according to D, because that D is some underlying distribution. Okay, so according to D. Okay, now there is let us say a label function f which detects whether an instance is inside the square or outside the square. Okay, so assume a label function f that determines or label function f that labels an instance as 1, that labels an instance as 1 if the instance is inside, if the instance is inside the square, inside the inner square. Okay, inside the inner square, or 0 otherwise. Okay, or 0 otherwise. So we have a distribution D, and we have a label function f, and we have these two concentric squares here. We have instances uniformly like that, and we have a label function that says, okay, you are this instance with this coordinate values. I'm going to label you 1. Okay, I'm going to label you 1, 1, 1, 1, so on. And these guys will say, okay, I'm going to label you 0. Okay, so these guys will be labeled 0. Yes. So we have domain data, which are these points. We have a label function which tells whether it's inside or outside, and we want to build a prediction function, okay, based on this data. So there is a label data, these data, and then whether they are inside or outside. So there is a training data at hand, and our goal is to learn a prediction rule that given a new data, okay, maybe this, and it will tell me, oh, okay, you must be inside. Looking at your coordinates, you must be inside. Okay, so that will be our new data. Okay, so let me put that as a circle, right? So that's the goal right now. Okay, so we want to and I started with something that ERM may fail miserably, right? And there is a concept of something called overfitting. So in view of this, I'm trying to explain where things can go wrong. Okay, things can go wrong when you are learning. Obviously, things doesn't go wrong. I mean, usually we don't say things go wrong during tenure. So we think that training data is a correct one. Okay, so usually when say things go wrong is using training during training. So let us build a prediction function on that. Okay, so let us say I propose a prediction function which will have a very low empirical risk, empirical error, or training error, whatever. Okay, so so let me propose a H which will do best on training data, but it will fail miserably on the test data. That's my goal. Okay, so like, can you think of that, right? Can you think of a prediction rule that will do perfect, 0 error on training data? At the moment I gave a point like this, which should have been predicted inside, but it won't do that. Okay, so what I'm trying to explain is, given a training data, you may end up producing an H which may be perfect for the training data but fails in the test data. Okay, that's another problem with when you are working with this type of problems. Okay, it is not necessary that you have to be the best. Okay, in a vague sense, like there are ways to like characterize this, what I mean by that, but being best is sometimes not good, because you will not generalize. Okay, generalization requires a little bit of flexibility in your model. Okay, so like I will explain this also with regression example, what happens there, but let us see in this case I will make it fail. Okay, so like fail in a big way. I mean, okay, so let us define an H hypothesis class. Okay, so HS, I mean, this hypothesis class will be very abstract. Okay, no one will kind of do like that, but this is like theoretical point of view. We will say, okay, we can make it fail, and these are the extreme cases, but it can happen in practice also. Okay, so what I'm going to write down will be very, very abstract in some sense. Okay, like you will say, okay, this is like just cooked up somehow, right? Okay, but let us see. Yi, if there exists I in the index set M such that Xi is X and it is 0 otherwise, okay, so take some time to think a little bit. This is what a learner produces, right? A learning rule, a prediction function. The learner has produced a learning function here for us, and just compare with this, and what can you say about the training loss, right? Will it fail does it have any non-zero training error, right? It doesn't have, right? So can you see that it does not have any, the way it's defined, it does not have any training error, because it's like explicitly pinpointed all those, right? It told us that, okay, pick all those which were in the training data, all those Xi for which Yi was there, okay, and otherwise you give 0 values. What did it do? It learned one-to-one mapping. That was bad. Okay, that's exactly what is bad. Learning very specific one-to-one mapping is not going to lead you to generalization. Okay, so now let me explain this a little bit more, like I told in words, but let us see. Yeah, I mean, yeah, I mean, I have to use this now. So let us see this one by one. So this hypothesis function, the prediction rule, what it says is that for x, okay, for an x, I am going to label it as yi if xi is if x happens to be xi. But this is exactly what training data is supposed to do, right? So what did you do? You memorized. So memorizing can be bad. Why? So the problem right now, the empirical risk is 0, no problem, right? Empirical risk is 0, you agree, right? Because you explicitly memorized. So each xi is labeled to yi, okay, because I specifically identified it hand by hand. Okay, so training error is 0. Okay, training error is 0 because if you look at the training error, then okay, since this is the first class, let us be a little bit slow also, it's fine. So so what was the training error, right? So set of all I in M for which HXI is not equal to YI, and number of those cases divided by M. But the way H was defined, there will be no cases where HI is not going to be equal to YI. Agree? There are no cases, right? Because for every YI, I have matched it with XI, right? So every YI, I have picked an XI. For every YI, I have picked an XI. I have picked an XI, okay, for which I have that corresponding mapping XI is YI. So what has happened here basically is X1 has been mapped to Y1, X2 has been mapped to Y2, XM has been mapped to YM. Explicitly here, we have done that. This exactly means this, one-to-one mapping. So if you see here, then there is no case here, it's a 0. The number of I for which xi not equal to yi is 0. So it's 0 by m, which is 0. So the empirical risk, training error, okay, empirical error, okay, the same thing, right? All this is, they are 0, right? So I have built a perfect prediction function by doing one-to-one mapping. But this is bad, okay, because one-to-one mapping is a memorization. Machine learning is not about memorization. Machine learning is about pattern matching, okay, understanding the underlying pattern and so on, okay. If it's memorization, then you don't need machine learning anyway, okay. So here we have memorized, training error is perfect. Now let us look into the test error. Okay, so test error. So the few remarks in words, right? So no matter what sample is, no matter what sample, so it's even independent of sample, right? This was one of the sample. You could have given some other distribution of the sample. I would have done the one-to-one mapping again the same way. So it's independent of the sample. Of course, finitely many samples. In practice, we always deal with finitely many sample anyway. So the point is, like, given any sample, I can memorize like this, especially in this case, the box example, okay. It may be tricky in some other case, but in this problem where we are saying whether the point is inside or outside, I am kind of memorizing it, okay. So no matter what the sample S is, okay, is even independent of the set S in this concentric square example. So no matter what sample S is, we have LS, the empirical loss, is 0, that we have proved above. So since the empirical error is 0, no classifier can be better than this, because loss is a non-negative non-negative number. So no other classifier can be better, right? So no other classifier. So this is the best classifier you can have smaller error. Okay, that's clear, because loss functions by definitions are greater than or equal to 0, and the minimum I got is 0, so I cannot reduce it further. So that's the optimal you can get. But let us check what happens to the test error, okay. So what happens to the test error or the true error, okay. So what about true error or test error? So what happens to the true error or test error on, so in general, what will happen if a new data point comes in? What will happen, right? It has memorized, I know. Okay, it has memorized on the given data, but let us say this new data came, let us say is our test data. So what will the prediction function, does the prediction rule know anything about this? No, okay, because it has memorized. It has not learned a pattern, it has just memorized. So it's going to do 50-50 prediction on this. Okay, it will do something 0 or 1. So it will have 50% chance of whether it's here or here. Okay, so the error will be here like 50%. Half of the time it's going to fail. Okay, so the fact that it has memorized but not learned any specific pattern, the pattern would have mean that it may have learned some, okay, may not say like the whole boundary, the class boundary, but maybe some approximation of the class boundary you could have learned. Okay, so H, the better H would have been something like this, that learns some boundary like this. Okay, in this case, ideally it should have learned a circle or something, but it's very hard in general to like get the exact thing, but maybe it could have learned something like this. And in these cases, yeah, it would have failed here, maybe the corner cases maybe, but it would have done pretty well on any other points. So these coordinates which kind of define the fact that they are inside the circle, it's going to predict them correctly, because it has learned a generic pattern and not memorized it. The fact that in this case it memorized it, now it's 50-50 game. It may be predicting correctly, it may not be predicting correctly, because these points are uniformly distributed. So they can be like, let us say the area is like kind of same, outer area, inner area is same, so it's 50-50 chance that point is here or here. Okay? It's like now it's a 50-50 game. Okay, so then in this case half of the time it's going to fail. Okay, the test error. Okay, so in words, any classifier that or I mean this classifier, right, not any, but it's like the classifier that we have right now. Okay, so a classifier that predicts 1 on a finite number of cases is kind of like half. So LD, now we are like asking for the kind of like the test error. So test error is done on data that is not seen, so underlying data distribution is like D. Okay, so that's like D. In the empirical we work with S, and when we go to the test, although we don't explicitly know the D, but that's what we are testing for. So that's the LD, but computed on HS. Okay, so I mean not computed on HS, but I mean the HS is the prediction rule that we found from the training data. So H obviously depends on S, and we are measuring the test error on HS. So this is going to be half, because the points are uniformly distributed, inner area is half, so it is going to do a 50-50 coin toss like prediction. Okay, because the probability that point lies here or here will be kind of like, probability that point lies inside is area of this divided by the total area, which is half. Okay, the probability is half of that. So which is very big error. Okay, so the test error is very big, like having a test error 0.5 is very big, right? It's like half of the times we are going to fail. Okay, which is very bad. Okay, so what happened here, right? What happened here is something called overfitting. Okay, this is exactly what is called overfitting. Overfitting is essentially a kind of something that goes closer to being memorizing the data. Okay, and that's what is called overfitting. Now this was a very specific example, but let me give you an example of something called line fitting. Okay, so you may have seen line fitting before, but let me give you another example of overfitting. Okay, so overfitting, let us say I have, like here I will do it in an intuitive way, not very. So let us say some people do experiments, okay, and they get a data like that. Okay, so for certain points, we have some observations here. Okay, for this point the output is this, for this point output is this, and so on. I am trying to learn a pattern in the data, so essentially I want to do some overfitting, fitting of the curve. Okay, so in this case these are our x1, x2, x3, and these are our y1, okay, y2, y3, okay, y4, and so on. Okay, so for a given x1 I have y1, given x2 I have y2, and so on. Okay, so here for a given training data we are asking what would be the hypothesis. Okay, so why it's called hypothesis? Because we will choose certain template, right? So we will use, in this case, maybe I will have a look at data because this is one-dimensional data, so maybe I can have some template in my mind. So in this case I'm thinking, okay, maybe quadratic type, because quadratic functions are kind of like this. So maybe quadratic, but it may be something else also. So that's called hypothesis, because I will start with a hypothesis. Okay, but I cannot start with any generic polynomial. Okay, even all class of polynomial I cannot consider. Okay, so I have to come up with certain template. So if it's a quadratic, so our hypothesis class, so let us say my hypothesis class is I can use theta notation also. Okay, yeah, so theta 1 x square plus theta 2 x plus theta 3. Okay, and this is my h theta bar, where theta bar is the vector theta 1, theta 2. Okay, so or like if you prefer, I can write this as kind of like theta 1, theta 2, theta 3. So this is my hypothesis class. This is my experimental data xy. Okay, x are these, y are these, and I'm trying to build a hypothesis class. So in this case I will come up with a template. So this template is a quadratic function, and this quadratic function is parameterized by these theta 1, theta 2, theta 3. Based on the theta 1, theta 2, theta 3, I can make this curve more up, bend more, okay, or maybe flatten a little bit. If you want to completely flatten, then theta 1 might be 0 also, then it becomes a linear. Okay, so so this is my initial inductive bias, that I come up with a hypothesis class which looks like this, and I have a I may want to kind of like now tune this theta based on the data. Okay, so I can do that now, because what I want from my hypothesis class is the following. So I want theta 1 x square plus theta 2 x plus theta 3 must match, for a given x, must match the y. So if it's given x1, then it should be equal to y1. Theta 1, so for x2 I want it to be y2. So this is x2, y2, and so on. Let us say we have m points. Ym. Okay, this is what I want my model to be, and I can use the usual numerical stuff that we learn in numerical analysis or whatever. It may not be possible that it's always equal. Okay, so we will formulate this as a least square problem. So it is like approximately this is what we want our model to be, to predict approximately this. So this is a least square problem. Okay, and the matrix here is like this. So you minimize this. Okay, this is an optimization problem, and you minimize over theta, obviously. So this is minimize over theta 1, theta 2, theta 3. Okay, so you will find a best possible theta, okay, by minimizing this. So you can use some numerical linear algebra technique like QR method, normal equation form, SVD. Okay, there are 3 ways to solve least square, right? So linear least square. So let us say I solve this. That's like optimization problem, right? So let us say I solve this, I get theta 1, theta 2, theta 3, then let us say those optimal ones are like star. So I put those star, and this is my learned model. Okay, now this becomes my prediction function, and then this is what I will predict. Okay, now during testing, someone can give me, okay, this is the new data point, then I will go up and check, oh, okay, this is what I'm going to predict. X star for a new data, I have Y star. Okay, so this is, now I told you that I want to explain overfitting in this framework. So how can overfitting happen here is if I kind of start memorizing. Like the previous example, what did it tell us? Memorization leads to overfitting. How can I memorize? I go hard with training, right? So how can I go how can I really go through all the points? By increasing the model, right? So I can increase the complexity of the model, right? Cubic, 4th degree, 5th degree, there will be a high degree enough that will make sure that it goes through all the points. So essentially what I'm doing, I'm memorizing. So it is possible that for higher degree, I will have a polynomial that goes through all the points. This is exactly what will may create, okay, overfitting again, because I went for higher degree polynomial, let's say x5 or something. It did go through all the points, but it may create problem for me because, as I said, we have memorized it, and the problem is that when we memorize it, if there is a new point, let's say here, okay, and this point was supposed to be here, okay, but so I am making a lot of error now, because the prediction would be this, and I mean the prediction by the hypothesis which is this h, and the actual point was supposed to be on the quadratic data. Okay, so you may say, like, you may say that why don't you memorize? What is your problem? Like in this case, let us say, previous case was an abstract example. In this case, you can say, right, why can't you memorize, right? What is the harm in memorizing, right? And the reason why we should not memorize is the data itself may not be very pure. That's also another thing. Like there are like two extremes. Previous example was a very extreme case, and the practical example is that the data itself may not be very, very perfect, in the sense that you are not supposed to memorize because the data itself has some error. So data was supposed to be here, but it's here. Data was supposed to be here, it's here. So the underlying pattern in the data was essentially quadratic. Data collection process went a little bit up and down, and you thought that no, I have to perfectly match the data, okay, which is you are not supposed to do, okay, because data collection itself has a little bit of error usually, okay. So then also it's not a good idea to memorize, okay, because there are a little bit of error in the data. So a data was actually quadratic. You thought, no, I have to pass through all this during the training, but then data was since actually quadratic, you did too much. Your prediction should have been here, now your prediction is here, okay, because you are following this. So in machine learning, these are the issues that can come. Even the data may not be like perfect and so on, okay. So this can affect your generalization. So here again, this is overfitting, because with a very large model, let's say 5th degree or something, I got this, but then my test error is bad now, okay. Training error is 0 because I passed through all the points. So hxi is yi, perfect, but then whenever a new point comes, I'm making a big error here. So these are my test error losses, okay. So here it should have been here, then these are my error losses, okay. So overfitting comes in very naturally in many experimental data like this, okay. So of course a general question would be, how do I know, okay, how do I prevent overfitting and so on. The general rule is that you do some validation, okay. So like I said before, you have this training data, and then you have like the test data also here, and you also do kind of like something called cross validation. So not just this one splitting of training and test data, you do the splitting next time something else also. Okay, so your training data becomes something else, you learn again and check whether for the test data it's giving you less error or not. So you do this test trend split multiple times, let's say k times or something. Okay, so after all this, that's your best bet. Then you can say, okay, now whatever I have learned, it seems to be optimal. And during this testing, training and testing, you play with these models. Okay, you say, okay, let me try square, let's see quadratic, what happens, let's see cubic, what happens, let's see test error. Okay, for different splitting, what happens, let me try 4 degree, let us do multiple test and train splitting, what happens in that. Okay, so this is all part of the training process, where you are tuning your model, you are trying to learn a best possible predictor function h. Okay, so this is all part of the training process. Okay, so there is a little bit of experimental maths, so both goes hand in hand in machine learning. Okay, okay, so I can define something called overfitting. I mean in formally. Okay, so what exactly overfitting is? So predictor whose performance on training set is excellent, yet performance on true data, I mean true data or the test data. Okay, let me use test data itself. Let us not introduce too many words. The test data is poor, is called overfitting. Okay, it's called overfitting. Now let us see empirical risk or the training risk, training error with the inductive biases. Okay, so the first example that I gave you for the square, that was the extreme case, and these are the cases where we have learned this. These are the cases where we see what happens with some of the inductive bias we have. By inductive bias we mean we are coming up with some template, and then from there, that template, we are looking at how the training and tester is going to behave. Okay, so hence there is a new section on this. It's called empirical risk, but I have already kind of given you a hint. So empirical risk minimization with inductive bias. So in this example, what you have seen is that the learner is choosing some template, right? In this case, the learner thought, okay, let me choose a class of polynomials, but it could have been anything, right? So this will be our hypothesis set, okay, hypothesis class from where we are going to choose a function. Okay, so learner chooses in advance a set of, all this has very underlying, very deep learning theory that maybe we will see today, but let's see. I mean, if you don't have inductive bias, will you generalize? Okay, I mean, like, what are the sufficient conditions you need, right? So we will prove some theorems, some learnability and so on. Okay, so we will see those things as we go ahead. So learner choose in advance a set of predictors So in this case, we have chosen a set of predictors. Okay. In this case, we said, okay, polynomial class. Okay. So, and we call this a hypothesis class called hypothesis class, and we use the notation H. Okay. So empirical risk minimization is over this hypothesis class essentially. So here, if I am saying quadratic, cubic, quintic, polynomials, so these are my hypothesis class. In this hypothesis class, I am trying to do empirical risk minimization, right? So we can write it in that way. So what we are trying to do, ERM is over the hypothesis class H for a given sample H, and this is argmin of small h in our hypothesis class H, for which the empirical loss is the minimum. So by restricting our hypothesis small h from this big H, okay, we are creating a bias. Okay, this is our bias, that no, I am only going to look for polynomial class of functions. Okay, so this is my inherent bias itself. Okay, because as such, fitting problem may be done by wide variety of prediction functions, but the fact that I am choosing a bias which is polynomial, this is called inductive bias. Okay, as a learner, you are imposing this inductive bias. Write this fact. All these facts are important for theory later on. Okay, so imposing a bias may be essential. Okay, so by restricting anyway you cannot search over all the functions anyway, right? So in practically you have to consider some bias anyway. Okay, by restricting predictor from H, we bias it towards a set of predictors. Okay, it towards a set of predictors. Okay, we bias it towards a set of predictors. So that's called inductive bias. So such restrictions are called inductive bias. Such restrictions are called inductive Okay, so when you read papers in machine learning, you will see many times they will say inductive bias. Okay, so basically inductive bias means, oh, I am taking a class of functions, right? So okay, and this inductive bias is done before the learner might see the training data. Okay, the learner may not know, the data is so complicated, learner may not even know, okay, what to choose in some cases. Okay, so you may start with very specific class of functions anyway. So it will be an intuitive thing. Okay, that's what I'm trying to say. If I'm going to test for papaya, then yeah, maybe I will say, okay, maybe linear function might do something. Okay, but in general, like it may not be fixed. Okay, so you may play around with various inductive bias. Okay, so these things are based on inductive bias is based on prior knowledge. Okay, so this is based on, so as I said, if it's image, then I will use CNN. If it's text, then I will use RNN, LSTM, and so on. So based on prior knowledge, So in the case of papaya, let's say we may have something like this, where let us say the softness criteria could be the first one, and then the color could be the second coordinate, and if it lies within certain region, right, so then maybe those papayas are tasty, right? So these are the tasty papayas, right? So we can kind of like, in this scenario, we may kind of like maybe plot the data a bit, and then maybe we can go with the hypothesis class of axis aligned rectangles in this case. Okay, so it seems to be, it may not be, because maybe a good classifier may be circular here. Okay, but so these are the things one has to decide. What am I supposed to do, right, with this hypothesis class? Should I go with axis aligned rectangles? Should I go with concentric circles as a set of hypothesis class, and so on? Okay. Okay. So yeah, so this is based on prior knowledge. So a fundamental question in learning is this. So fundamental question. So over which hypothesis class E R M H learning will not overfit. Okay, so one of the questions is like, over which hypothesis class the learning algorithm will not overfit. Okay. So one of the cases where it may overfit is when you allow any arbitrary hypothesis class. Okay, so any arbitrary hypothesis class will certainly overfit. Okay, so for instance, in the previous example that I said about this, if I allow it over all possible rectangle, okay, if I allow it over all possible rectangle, it's going to overfit. Again, it will memorize. Okay, so it will memorize like this. Okay, so it is quite clear that when we are learning, when we are designing a learning algorithm, we should not allow arbitrary hypothesis class, because if we allow arbitrary hypothesis class, it will memorize, and if it is memorizing, it will overfit. So the fact that I keep a hypothesis class as finite will help me not overfit. Okay, that's important, right? So one thing is clear, from learning theory point of view, you should keep a check on your hypothesis class dimension. If you allow it to take anything, it will certainly overfit, because it will lead to memorization, right? So from here we see at least one handle that learning may be good. It seems like we have to fix the number of the hypothesis class, okay, or keep it finite. Okay, so for instance, some of the simple restrictions could be like upper bound on the size, upper bound on the polynomial degree. Okay, so these are the restrictions you may have to do. Okay, so example, upper bound on degree of polynomials in case of fitting problem. Okay, the fitting example that we saw before. I think we can stop for today. It's almost close to 2 hours, and we will continue with this in the next Wednesday. This is only weekly. Okay, so we will do it on next, but it's 2 hours usually. Okay, so for those who are new, let us take some time to kind of like understand this is more or less machine learning. How we formulate it is in maths terms. So I think with this I will end the lecture.